Okay, good morning. We are going to continue to finish that review that we started the other day. We talk about we talk about the concept of the functions, okay, and we try to give you some uh, proper or famous functions that we're going to use. Okay, we talk about the polynomials, rational functions, radical functions, and we end up with a piecewise defined function. Okay, so the last example that we did is this one, which is going to be very important for us. Okay, if the function is defined by more than one equation, so we say this function is defined piecewise or a piecewise defined function. So it's very important to be able to graph it, okay, and read the information from the graph. The first one that I gave you was just two pieces of straight lines, but the curvilinear one, we cannot have quite a lot, but there is just a couple of them that would be useful, especially this one. This is one of the problem in your book. And this example comes from time to time. So let's continue with this one. We want to sketch the graph of this function, okay? So you have three parts. When x is less than, so the solution, I just continue what we did the other day. Okay, so the solution is going to be, if you want to think about the type of function that you have, so this is going to be number line from negative infinity to positive infinity. So this function is partitioned at 0. You see it's going to be this 0. So this is 0. Then in this portion, if x is less than 0, the function is just y equal to the x, okay, a straight line. And when x is bigger than 0, the function is a curve. It's going to be x squared, is kind of parabola. But at x equal to the 0, the function is equal to 2. So if it's going to be y is equal to the 0, so you have simply y equal to 2. So you have three portions to consider, okay? 1, 2, 3. So we go with the first one. The first one is y equal to the x, so this is going to be y equal to the x. Okay, with the restriction that x is less than 0. We talked about it the other day, we need just a couple of points. So this is going to be x and y. So we talk about you must start with the partition point. So it's 0, done. 0, done. Something like a negative 1. You can pick any number you like, but you must start with a 0. Okay, so the function is, the equation is y equal to the x. So if you substitute, that gives you 0. And if you substitute negative 1, that gives you a negative 1. Okay, so we're going to go and graph this part. And then we come back and we continue. So this is going to be the graph of this part. Okay, so you have a point at 0, 0 here. So this is going to be 0, 0. So you check to see if this point belongs to your graph, because that's a partition point. X is not equal to the 0. Thus this point is not going to belongs to this graph. So what you have to do is you have to make a hole here. Okay, so you have to check it. If it's going to be equal to, so you cover this point, you make it solid. But if it's less than 0, it's strictly less than 0. So this means 0 is not going to be on this part of the graph. Okay, then we get the next point. It's going to be negative 1, negative 1. So this is going to be x equal to the negative 1 and y equal to the negative 1. You connect them together. This is the second point of your graph. But remember, you are going to go to the left only. So left only, this means this is going to be the graph of the, okay, so this is going to be the graph of your function for this part 1, if you like. Okay, any question? So we talk about it, you must start with this 0, because you have to give us what would happen, you know, when x get close to 0, or you have all the information regarding this part. Now we go back and we get the second part. The second part of the graph is just 1 point, you see, 0, 2. So in the second part of the point, a graph, when x is equal to the 0, so you have simply y is equal to 2, nothing else. So this part is just 1 point, 0, So go back, identify it. That's 0, 2, 0, 2, 1, 2. So this is going to be the graph of this part. Just 1 point. Any question? Okay, so that gives us a 0, 0, 2. Then we go to the last part of the graph. So it's going to be the last part of the graph. It's going to be a curved linear. It needs more attention. So y equal to the x squared. But what is the restriction? The restriction is x must be a positive number. Okay, x must be a positive number. So what you are going to do is just pick a couple of points again. So this is going to be the case. You have the x, and this is going to be y equal to the x squared. Again, you have to start with the partition point, which is 0. 0 up. Up means a number greater than 0, like 1. This is x squared. When the power of the x is not 1, so this means that this graph is going to be a curve. It's not going to be a straight line. So if you need, you may pick more points. Okay, so you try to graph it as is, but if you need points, more points, you come back and you get more points. Okay, so x equal to the 0, you substitute, that gives you 0 here again. And x equal to the 1, you substitute, and that gives you 1 squared, which is equal to 1. Okay, go back to the same graph, identify it. So we start with the 0, 0 again. So this is going to be 0, 0. But do you have it? Do you cover it? There is no equality sign. So you are going to just start from here. You cannot have it. Okay, so that would be your starting point. Then you get to the 1, 1. This is it. This is going to be 1. And this is 1. So this is going to be 1, 1. Remember, your graph starts from here and it's going up, 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 up. It's a parabola. It's a parabola, you know that, so it's not going to be a straight line. So it's going to be kind of, you see, this is going to be your graph. So one part of the graph, you see one part of the graph is going to be a straight line. This is going to be the straight line that you're going to have. Okay, and one part of the graph is going to be a curve. So this is going to be interesting graph for us. And the reason is that, you see, when we get to the 0, if you want to find what is going to be the value of the function, you see the value of the function is not going to be found from the first part because this is empty. You cannot find it from the second part because this is empty, but the 0 is up here. And that would be when we get to the notion of the limits today. And this would be very interesting example for us. Okay, that's why we like it. And we are going to use it. So the value of the 0 is good. And again, you see, you get a solid point over here. So this must be a hole because, as you know, if you get any vertical line, that vertical line can intersect the graph at one point only. So you cannot have two solid points at the same time. So this would be interesting for us when we get to the, okay, by the end of today, we come back to it again for this function. This function, at the end of the day, we say the limit of this function at 0, we can estimate the value of the function at 0. But the value of the function is going to be different. There is something interesting about this one that we come back to it. So there are a couple of them in your book. So you have to pay attention to this type of graph and make sure, you can get more points to graph it. But if you don't start with the 0, you will lose the graph. Okay, so partition points are going to be very important for us. Any question? So get to know this one and be prepared to graph it for us and read the information from the given graph. So that would complete our review of the notion of the function. So that would enable us to start talking about what is going to be calculus. Okay. So this is the review one. Just study this one, and we have a couple of problems in the practice quiz that you have. And of course, we are going to give you one question of this one. Okay. And we are going to see 3 more times in this course. The same thing, but different interpretation, different Okay, different concept that we refer to it, but it's the same thing. Okay, any question? So let's see what is calculus. So officially, this is going to be our first section. Okay, so we are going to talk about calculus. So that would be official term. And basically, so what is calculus? So this is going to be, I'm going to do it all together. It's going to be start from section 1.1 and we end up with the 1.3. Okay. I put everything we need together so that give you an idea of where you can find it. Okay, so let's preview what we are going to do in this course. Okay, so what's going to be the preview? Our preview is if you want to find what is calculus. You see, calculus, if you check, in your dictionary, they are going to give you the calculus is going to be a small pebbles, okay, that you can use in order to calculate, if you like. That's the term from dictionary. But from our point of view, calculus is a study of rate of change of the value of the function. You see, whatever you do in algebra, when a function is given to you, f of x equal to 2x plus 1. The best thing you can do in algebra, you just find the value of the function. You find f of 2, f of 5, f of 3. When you find f of 2, f of 5, f of 3, you're just dealing with the exact value of the function. That's the exact value of the function. But, and this is something belongs to the past. So for example, if you have a formula for the C of X, cost of producing X number of the cars, if you want to find C of 100, that would be the cost of producing 100 cars. But what we would like to do in calculus and in science is the prediction. Okay, so in calculus or in science, you predict something. You see, you collect some information about the coronavirus, for example, and you predict what would happen in the next 6 months. That is the rate of change of the growth of the coronavirus. Okay, so that's the action of calculus. Calculus is an art, if you like, an art of estimation. What are going to estimate? You estimate a rate of change. Okay, what would happen to your function in future? Just make sure to get this idea, the difference between the algebra and calculus right at the beginning. Okay, so in algebra, something happened in the past and you find the exact value. But what are going to do in calculus or in science? You start with something, but you're going to study, collect information, and based on that information, you are going to predict what would happen in the future. Okay, so that's the best interpretation of calculus, really. So that's it. So if somebody, when ask somebody what's calculus, they may give you some formulas. But in everyday life, in your family, your friends, somebody from other discipline asks you, what is calculus? So you should be able to connect to the everyday life. Calculus is the study of rate of change of whatever we do. You know that whatever we do is going to be a function. So it's a rate of change of it's the study of rate of change of values of a function. And this is what we're going to do. Calculus is, if you want a kind of terminology, calculus is the study. Okay, the study of, they call it study of change, but I say study of rate of change. Rate of change. That's the general expression that we use for calculus. The study of a rate of change of values. Values of a function. Of a function. That's the definition of calculus. Okay. So what is this calculus about? The calculus would divide it in 2 parts in this course. Okay, so that's going to be what we are going to do, calculus, and then we continue calculus 2 and 3. What is going to be calculus? Calculus we divided in two parts in this course. The first part of calculus, every part of calculus, you usually start with a problem. With the problem in science, in geometry, okay? And then we come back and we take care of it. And so the first part would historically solve this problem. Okay, the problem of this is the problem, we call it the tangent line problem. What is going to be the tangent line problem? I'm going to explain it, but I'll just give you the idea first, okay? So we are going to introduce what is going to be the tangent line problem, and then we're going to solve it. And the part of calculus, okay, the part of calculus that will deal with this problem, okay, is going to be referred to it as differential calculus. So it's going to be differential. I explain it why we are going to call it differential calculus. Okay, differential calculus. So this is going to be the problem that, you know, you have a given curve and you want to find what is going to be the equation. Okay, what's going to be the equation of a tangent line to that curve? In order to find it, we are going to introduce a notion that we call it the derivative of the function. And that's why this part of calculus would refer to it as a, okay, we refer to it as a differential calculus. Okay, that's first part. That takes you through the calculus 1. The first 5 chapters of this book are going to be related to the solving this problem. Of course, this is an excuse. And then we apply it into the different part of science. Okay, and then we are done with this problem, that there is going to be another problem that we're going to solve. The second problem is going to be called the area problem. The area problem. So what we are going to do is a region would be given to you. Then you would like to find the area of that region. If the region is a triangle, for example, you can find the area. If it's going to be a rectangle, you can find it. But if you go to the beach, okay, the beach, the shoreline are not going to be just straight. It's going to be a curvilinear one. So how are we going to find the area over there? Okay, in order to get that area, again, we estimated in calculus. Okay, we estimated, we consider the rate of change of that area. So in this part of calculus, we need a machine. The machine will be called integral. And this part of calculus is called integral calculus. Integral calculus. Okay, so the integral calculus is part of calculus that refer to the problem, to the area problem. Okay, so that would be integral calculus. And the part of calculus that will solve the tangent line problem for you is going to be called differential calculus. In calculus 1, you are going to get an introduction of this one. Basically in your book, it's going to be chapter 4 and 5. You get the introduction. You'll be able to solve the area problem. But in order to complete it, you have to take calculus 2. So the calculus 2 mostly would be talking about this notion of the integral. And of course, again, the area problem is an excuse. This would be referred to the various other parts of science, depends where you are. The foundation of a statistic is going to be integral. And then when you take it in calculus 3, most of the calculus 3 is going to be notion of the integral. Then we use the notion of integral to explain everything. Okay, to explain gravity. Okay, there are various problems. There are various. I'll talk about it later on for you. We call them vector fields, and then you will see the application of this type. Okay, so in calculus 1, a brief version, but in calculus 2, all the calculation. In calculus 3 is going to be, of course, in 3-dimensional in a space. Okay, so that's going to be the road plan for this course. Any question? So calculus rate of change. So what we're going to do, we're going to start with this problem. Okay, we don't want to just write on, give you a formula, okay, memorize it. No, it's not going to be the purpose of this course. It's going to be the concept that's going to be important for us. Okay, so we get the concept, and then at the end of the day, there is a formula. Then, like a machine, you use the formula over and over and over, and you're done. But at the end of the day, you must get the concept for your application in physics, mechanics, biology, business, etc. Okay, so you let me know anytime you have a question. So let's continue, take the first problem. What is the first part? So we are going to be stay with this one for the next probably 3 weeks. Okay, then for the other part of the course, we take care of this. Okay, so what is the tangent line problem historically? So what is going to be tangent? Again, be patient. Okay, then we get some shortcut at the end, but we are not going to rush. Okay, because we need to understand it. So what's going to be tangent line problem? You see, this problem was around for many, many years, and Isaac Newton, great British or English mathematician, was the one who solved this problem right at the beginning. There are some other people that done it, but mostly Newton is the one, or no Newton. Okay, so what is this problem? Easy problem. A curve would be given to you, would like to find the equation of a tangent line. So the problem is find, okay, find the equation, find the equation of a tangent line, equation of a tangent line. Okay, tangent line to the graph, some easy graph, the graph of the function. Okay, the function is y equal to the f of x. Okay, and we want to do it at a point, with the x coordinate of a. You see, that's a famous original problem of the Isaac Newton. What is going to be the equation of a tangent line? Okay, so let's do it. Let's see how we're going to solve the problem. Okay, so let's see what we need. Solution. So to get a better understanding, let's have a graph here. Okay, that's it. So suppose this is the given curve. Okay, this is the given curve, and we have a point x equal to the a. So this is going to be x equal to a. Okay, that's going to be a. And you know that you can find a point with the coordinate. So we drop the x into the function. Okay, so we get f of a. Then we are going to have a point here, and we call this point P. Okay, so I have the point P. So that's the first thing that I do is I just substitute, okay, to get the point P. So I have the A and the F of A. Okay, that's going to be the point. So what I would like to do, I would like to get the tangent line. So if this is going to be the tangent line, suppose this is going to be the tangent line. And what we would like to do, we'd like to find the equation of a tangent line. So that's going to be the point P that I have with the coordinate of the A and F of A. Okay. So I create a point here. So this is going to be a point that I have. Okay. Let's check some of your information. Yeah, you want to write the equation of a line. Do you remember what you need for the equation of the line? Any suggestion?
Slope.
Excellent. We need the slope. So the slope is missing. So we need the slope of a tangent line. Very good. So if we have this slope over here and we have a point, then we can write the equation of the line. What's the equation of the line?
Y minus y1 equals mx minus x1.
Excellent. So note that if we have this information, then we use this formula, y minus y1 equal to the m times x minus x1. Okay, this is going to be is the equation. Okay, it's going to be the equation. It's going to be the equation of a line. Okay, so if we set up everything all right, then basically what we are going to have is going to be this one. So this is going to be the y. Okay, y1 would be just f of a. Okay, that would be f of a. And then m is going to be the slope of a tangent line. Okay, then you get the x minus a. Okay, so the problem is going to be finding the slope of a tangent line, because I've already got the point P. Okay, I've already got the point P. So if I can find the slope of a tangent line, then I'll be able to do the job. So the problem was, what is, okay, what is, so the question, the main question really is for them was, so this is the formula, okay, to find the slope of a tangent line. The question is, what is the definition of the tangent line to the graph of this function? You see, historically, the question was, what is the tangent line? What is the tangent line? You have to find out what is the tangent line, then you'll be able to find the slope of this tangent line is given to. Any idea what is the definition of the tangent line?
It would be the derivative.
What do you mean by derivative? No, we haven't got to that part. We want to do it historically. Just what is the definition of the tangent line? Because eventually the derivative is going to be the slope of a tangent line. So why is the derivative the slope of a tangent line? We haven't talked about derivative. Okay, we want to know how historically how they did it. Okay, so their question was this one: what is the definition of a tangent line? Okay, any suggestion? Let's see how they find out. So out of calculus, where do you see tangent line? Or when you have heard about tangent line? In which discipline, which part?
Circles.
Excellent, circles. So that's it. Let's go to the circle. So let's go to the circle to see what would happen at the circle, then we come back. Okay, note that. Okay, if a circle is given, if a circle is given, you see, in the case of the circle, this is the situation that we have for the definition of a circle, the tangent line to the circle. So if the circle is given to you, and this is going to be the point P on the circle, okay, the way they defined, this is going to be a center of a circle. The way they define the tangent line in geometry is they say we start with the circle and we start with the line. Okay, we pick a line outside, okay, a circle, it's going to be the line. Okay, and then what we'd like to do, we'd like to make this line to be a tangent line. The way they do it, they say that we are going to move this line towards the circle. Okay, so it's going to be the one, and then we get a point P here. Okay, that's going to be the point P here. So what we're going to do is we are going to move the line to intersect the circle at the point P. You see, this is going to be the way we do it. Okay, so that was the point P. So intersect the circle at another point. We call it the point Q. Okay, so we create, this is the first time we are going to intersect the circle. So this line is going to be called, okay, the PQ or QP. PQ is going to be called the secant line. Okay, that's going to be the secant line, because it's intersect the circle at 2 points. But in order to be able to get the tangent line, the way they do it, or we do it in circle, we move this point Q towards the P. Okay, if you move it, you are going to get this type of lines. Okay, so that was this is the circle that we did have. Okay, and that is going to be the point P. Okay, so if you, and that was the original, that's the original Q, if you like. That's the original Q that we have. So what we're going to do, we're going to start moving it up. If you move it here, so this is going to be the line again, the second line, and then you move it closer and closer. So this is going to be the case. Okay, so this is going to be your Q, and this is going to be your Q. As you can see, if you get closer and closer to the point P, eventually there is going to be the case that this point Q is going to be the same as the point P, if you like, and that would give you the tangent line. This definition of tangent line is circle. So the case that they did it is this: if the point Q is going to be approaches P, if you like, getting closer and closer to the P, then this secant line would becomes the tangent line. So that was the idea was used by Isaac Newton, and before him, of course, is used by his teacher, his mentor, if you like, to get this one done. So if we continue with the same idea here, so this means so we have the secant line would be the same as the tangent line. So in this case we find okay, so if they are going to be the same, so they should have the same thing for the slope. Okay, so let's find out what's going to be the slope of the secant line. Okay, so remember the P is going to be the point like A and F of A on the case of the graph, and the point Q is just arbitrary point. So it's going to be X and F of X. Okay, so I have 2 points. Do you remember the formula for the slope of a line when 2 points are given to you? You remember that formula?
Y equals mx plus b.
No, the formula for this slope when 2 points are given to you. We call it 2 points formula. Rise, run, remember?
Oh, y1 minus, or y minus y1 over x minus x1, or yeah.
Yeah, that's it.
Okay.
Rise, run, yes. Y2 minus y1 over x2 minus x1. Because that's going to be the rise, run. You know that there's going to be the rise, run. So it's a y2 minus y1 over x2 minus x1. Okay, in the case of our case that we have is going to be this slope of a secant line is going to be, you see, f of x. This is going to be f of x minus f of a over x minus a. Okay, that's going to be the slope of a secant line. Now, let's go back to see what would happen if this Q goes to P. In a case of that we did have, you see, that was the idea for the circle, and they used the same idea for our graph that we did have. You see, that's a graph that we did have. So what we did really is, this is the point P, so this is A. Okay, that was over A. And this is the point P. So we pick an arbitrary point. Okay, this is going to be the point for the arbitrary one. So since arbitrary, we put it's going to be equal to the X. So this is going to be your Q. And that is the secant line in this case. Okay, that's a secant line in this case that we did have. Okay, so we just move it closer and closer, and eventually we get that tangent line here. Okay, that's a tangent line. So in the movement over here is, you see, this means Q goes to, see, Q getting closer and closer to the P. this means this X getting closer and closer to the A. Because when you move, you see when you get different Q here. So in that case, X getting closer and closer to the A to get eventually that part. Okay, so we go back, we say, okay, this is what we know so far. If the point Q getting closer and closer to the P, then the slope of the secant line PQ is going to be almost like the slope of the tangent line. Okay, so what we are going to get over here is that if you want to X getting closer and closer to the P, you have to pick the value of the X to be. So equivalently, if you like, the case is going to be that if X is, we say if X is approximately equal to the A, very close to the A, then the slope of the secant line would be approximately equal to the slope of a tangent line. You see, so basically this means if X getting closer and closer to the A, then the slope of a secant line, of course, is f of X minus f of A over X minus A. This is going to be the slope of a tangent line. So this is going to be our first interpretation, if you like, of the idea of the estimation that we're going to do in calculus. So basically, we estimated the point A would be given to us. We go around the A, and we check all those secant line over here. We check the secant line, and eventually, when X getting closer and closer to the A is a fixed number, like 2. If A is equal to the 2, when X getting closer and closer to the 2, so we are going to find this quotient all the time. We find this quotient all the time. The values that we find may be all rounded up to the 5, if you like. If they all rounded up to the 5, then 5 is going to be the slope of a tangent line. This is just interpretation that we're going to have, but eventually we are going to introduce the notion limits later on. But we are going to write in future. This is just for information for the time being. The slope of a tangent line is going to be, we write the limit of the f of X minus f of A over X minus A when X goes to A. We're going to explain it. But that is historically what would happen right at the beginning of calculus. And this is the way they find out that they should focus on this quotient. If they want to find the rate of change, and if you want to find this is just, this is just a game for the time being, just focusing on the equation of a tangent line. But that would give us the hint, the way we're going to do it. So we have to take care of this estimation that we talk about it to be able to get the idea. Yes, of course, this is not going to be easy, if the function is going to be complicated. So that's why we are going to take this notion in future and we call it the derivative of the function. Not now, remember, the derivative of the function. So we introduce the derivative and eventually we'll be able to solve the problem of a tangent line. That's why we call it differential calculus, the part of calculus that refer to these ideas. Okay, any question? So that's just give you an idea, the method that we're going to use in order to take care of our job, if you like. This is the rate of change that I talk about it. You see, calculus, we call it, is a dynamic part of mathematics. Algebra is the static part. In algebra, you don't move. See, if the function is given to you, find f of 5, done. Is the exact value. But in calculus, it's different. In calculus, you move to be able to get it. So this is the dynamic part that, we start with the point and we estimate it getting closer and closer to get the values. So that will tell us something that we have to focus on this. So that's why we are going to introduce this one later. And before getting to that derivative, we have to focus on the action of the limits to be able to do it. Okay, so I'm going to give you one example, and you have a couple of examples in your book. Be patient. We are not going to do this sort of operation on the test, on the quiz, but regarding just a couple of examples that you have to follow the instruction. Don't rush for the derivative. There's no derivative here. Okay, you have to find this slope of a secant line, as I'm going to do it for you, and you put them together. It's not going to be given to you on the test, but give you better understanding of the concepts that we're going to have. Okay, any question? So let's do one example for the sake of this section. Okay, but then we come back to it. So that give an idea of the birthplace of calculus, if you like, and the way they did it. Then I'm going to give you various examples in everyday life, how we're going to get to this one. Okay, so to solve the problems of this section for a while, I give you one, but be patient. At the end of the day, we are going to have a nice formula to take care of it. But keeping with the introduction, so again, this is the example of historically the first one that was done by, again, Newton. So that's the question. Now the real one we want to find, and you have a couple of them in your book. Okay, find the equation of a tangent line. Find the equation of a tangent line. Okay, find the equation of a tangent line to the real graph. To the graph. To the graph of this function, f of x equal to, it's mostly parabola, x squared at a point. Okay, at a point with x equal to, let's say, 3. Okay, let's see how they did it at the beginning. No formulas, remember. So at this level, if you want to do it, you have to do exactly what we did. So that would be the solution. Remember, we need a point. We need a point. So what is the point? Point need x and y coordinate. X is equal to 3. You substitute here to get the y. Okay, so we need the point. So this is x is equal to 3. I substitute, f of x would be 3 squared, which is equal to the 9. Okay, so I have a point. So the point P, the coordinate of the point P would be 3 and 9. This is going to be the first step, the point. Any question? Next, the slope. The slope. Remember, this is just the beginning. Don't rush for the derivative, just the formula. So we know how we're going to find the slope. In order to get the slope, you have to find the slope of a secant line first. Okay, so you have to find the slope of the secant line. So you need to pick a point Q. The point Q is going to be x, arbitrary x, and the function f of x. So your x is going to be x and f of x, which is x cubed. And your point P is 3 and 9. Okay, find the slope of a secant line. MPQ is equal to, we talk about it, y2 minus y1, or in this case, f of x minus, you see f of x minus f of 9. You have the point, you can write it down. y2 minus y1 if you like. So MPQ is going to be equal to, that's it, y2 minus y1 would be, sorry, that's x squared. X squared, so it's going to be x squared, okay. And that's it, 3, I missed everything. X squared minus 9 over x minus 3, that's going to be the slope of a secant line. Okay, so this is going to be the case. We can simplify it a little bit. So the top would be x minus 3 times x plus 3. Okay, that's going to be x minus 3. And we can simplify it, but we have to consider the fact that x is not equal to 3. You have to mention this one because we estimate. Remember, we don't care about x equal to 3. We're just estimating around. So you simplify it, but you have to focus on the fact that x is not equal to 3, because if x is going to be equal to 3, that would be 0, 0. Okay, so the slope of a tangent line, the slope of a secant line is x plus 3. X plus 3, but when x is not equal to 3. Okay, now what is going to be the slope of a tangent line? The slope of a tangent line, the slope of a tangent line, as we talk about it, you estimate this one. It's going to be the limit, if you like, informal limit, x plus 3, when x goes to what? X goes to 3. Now you have to do those estimation for us. Remember the way we did it from the geometry point of view. We pick a point close to the 3 and we find the value of x plus 3 to see if they are going to be rounded up to a fixed number. So again, for the time being, you have to estimate this, just pick some points. So we have to draw a chart, if you like. This is going to be the chart. So you pick some x and you find the corresponding values for the function, okay, for the x plus 3. Remember, you want to estimate it around 3. You see, this is going to be, this is what we have. So we have the 3. So you have to go from right or left. When you estimate up or you estimate down. But you're not going to use the 3. Okay, so this is going to be the way I'm going to estimate it. I'm going to estimate it from this direction first. So I start with the 3, but I'm not going to use the 3. But I pick some numbers close to 3. Okay, but from the right. Give us a number. Pick a number. A number close to 3 from the right.
From the right,
Very
would-
cool.
3.01. Oh,
Yeah, 3 point, 4 is, 4 is not bad, but we pick the numbers up to the 4, okay? So like a 3.001. Okay, so if you substitute here, so that gives you 6.001. Okay, then we can, you can pick some other points, okay, which is going to be much closer. Okay, so if you move on, okay, if you pick something like 3.002, for example, that gives 6.002. Okay, and then you can pick on, something like if you pick 3.5, for example, that gives you 6.5. And if you pick the 4, which is going to be equal to the 7. So as we can see, when we get closer and closer to the 3 from the right, if you like, these numbers would round up to, you see, that's 6.02, 6.01. So they would be round up to the 6. Okay, so this is the way we're going to write it down. We say we estimated the limit of x plus 3. We let x goes to 3, but from the right. From the right, we write it down as a 3 positive here. Okay, 3 positive from the right, and we get the 6 here. That would be our right estimate. I want to just give you informally something that we are going to do it later on. Okay, we are not done. You have to pick, and this is the way you are going to do it. A couple of examples problem that you have in your section 1.1. Okay, you have to pick some numbers. In some of them, the numbers are given to you. You better do a couple of them, just get the idea. But we are not done. We have to repeat it again. But this time from the other direction. That's again the x, and that's going to be x plus 3. We want to pick the numbers less than 3, so we pick the 3 here. Now we go from this direction. You may go up to the 2. Okay, just pick some numbers close to 3 from the other angle. So if x is equal to 2, 2 and 3 would be 5. So if you get something like 2.5, so that gives you 2.5 and 3 would be 5.5. And if you pick something like, 3.7, I'm sorry, 2.7, that give you 5.7. But if you pick something like 2.9, that give you 5 point. Okay, if you get this one, that give you 5.9. And as you can see, again, when you round up these numbers, this would be round up to the 6 again. Okay, so from this direction, from the smaller values, x goes to 3 negative, that gives you 6 again. Okay, so we say that from the right and the left, we just estimated with some numbers, and we end up with the 6. So the conclusion is going to be the limit or estimate. X plus 3, when x goes to 3, is going to be equal to the 6, and the 6 would be the slope of the tangent. Okay, any question? Again, we are using the basic ideas. Don't worry. Don't say I can use it with a shortcut in 2 seconds. Yes, we do it later. But we want to use this one to get the idea, to know it. And there are some functions that you have to do, step of operation to get it. But we are not done. Remember, we are interested in the slope, the equation of tangent line. So we have a point now. We have a point which is going to be 3 and 9. And we have the slope of a tangent line, which is equal to the 6. And we know the formula for the equation of the, okay, the equation of the line. That's it. Y minus y1 equal to the m times x minus x1. Substitute, simplify. Y minus 9 and the 6 times x minus 3. You have to simplify this one. Okay, I simplified here. So that give me y minus 9 equal to the 6x minus 6x minus 18. We move the 9 to the other side. So that gives us a 6x minus, okay, 6x minus 18 plus 9. So y would be 6x minus 9. So that's officially is going to be the equation of the tangent line. Okay, so that is the equation of the tangent line. And we are done. Okay, so that's history. That's history, but give us something to start with. That what we should focus. We should focus on this estimation over here. Try to simplify it. Because this problem was easy, x squared. But if things getting complicated, of course, we cannot use all the time using calculator to be able to do it. So what we have to do, we have to go back and take care of these estimation that we do over here to get to know it. Any question? So that was history. So what is going to be the road plan now? The plan is, let's go back and take care of these estimations, these limits, to make sure we understand it. And then we come back. When we do the limits, eventually we define the derivative of the function, kind of in 2 weeks times. Then we come back to this problem and we use the derivative to find the slope. But you have to take care of this estimation that you get over here, the rounding one. Any question? So what we are going to do is officially, we are going to give you what is the limit of a function. Okay, what is this estimation means and how are we going to do it to get the idea when you say rounded up. Okay, but before I give you that one for fun, it's not bad. I usually ask this question before getting to the, okay, so the next concept is going to be the limits. We polish everything really, but I usually ask this question. I teach at university. I teach to the future teachers. There is a course. It's a Math 311. If you want to be, to get a certified, to be certified to be a teacher, you should take this course before you graduate. I teach that one every semester at Cal State San Marcos. And so there are something in their books really quite interesting that I emphasize that is calculus. One of their problem is this one. Just for fun, is not bad before getting to the limits. That give a very good idea of how we're going to operate. Okay, so let's answer this question. I want to know what's your idea. This is the question that I talk about it for them and emphasize that if they want to be teachers and if you want to explain this concept, because they are going to be teachers of the lower grades, if you like. How are you going to explain this type of things when you are going to be in lower grade? And this is one of their problems. Okay, and so I'm going to ask you this question. Let's see how we're going to round these numbers. You see, round 1.46. Okay, up to the, let's say up to the 10 place, 10 place, 10 place, or up to the 10th, if you like, 10th place, 10th. Round it up to the 10th place. Any suggestion? Round it to the 10th place.
1.5.
Very good. 1.5. Yes, 1.5, 1.5, 1.5. Yes, 1.5. That's it. So 1.46 would be approximately 1.5 when you round it to the 10th place. Okay, why it is 1.5? What's the meaning of this that you did? Any suggestion?
It's closer to 1.5 than 1.4.
It's closer. Okay, what is that 10th place means?
The first number after the decimal.
No, no, that rounding one. You see that the expressions. What's the meaning of rounding? That's, that's the idea that we want to know. Can you give me another number that if you round it, you get 1.5? Another number?
1.47.
1.47. 47. Very good.
1.52.
No. Oh, okay. Round it up to the,
Oh,
No,
sorry, that was round down. That was my
no,
bad.
no. Anything else? 1.4, yeah, 1.49, 1.49. Anything else? You missed one of them. Any other number to get a 1 point? You missed 1 point. Yeah, 1.48. 1.48. 48 to be 1.5. You see, these are going to be the one that you are going to get back to the. So when we round it up to the 1.5, there are many numbers, if you like. You see, there are going to be many numbers that if you round it up to get the 1.5. But the idea is, that this is exactly what will happen. You see, this is going to be the target that you have over here is going to be 1.5. You see, that's going to be 1.5. If you get a 1.5, you estimate these numbers to get to the point of 1.5. You see, the one that I would like you to know, this is the 10th place that we are going to talk about. What's the meaning of that 10th place? You see, when you round the numbers, you may, rounding is an estimate. Okay, you may lose something or you may gain something. Okay, in the case of the rounding. So in this case, you see 1.46, 47 to get a 1.5. This is where you gain something. But there is going to be the case that you may lose something, but you get a 1.5. You see, if you get something like 1.1, 1.2, 1.53, 1.54, then if you run that up to the 10th place, you get a 1.5 again. So what is the meaning of the 10th place? When you say to the 10th place, This 10th place is going to be your tolerance. This is how much are you going to prepare to lose or are you going to prepare to gain? You see, we say up to the 10th place. So this is if you think about it, these numbers that you got, you see the difference between the 1.5, this is going to be the estimate, and the exact one, which is the 1.46. In all the case, the difference between these are going to be less than 1/10. And the reason that we do it is that this is the 1.5. Since it's the 10th place, this is the 110. So 110 is going to be 0.1. If you divide it by 2, that gives you 0.05. So you got this is a 1.5. If you add it, you see 1.5 plus 0.05. That gives 1.55. So at most, if you go to this part, you see at most, if you go to the up to the 1.55, and on the other direction is going to be 1.5 minus 0.05. Okay, if you get back to the other direction, that gives something like 1.45. I think that's going to be 1.54. Yes. You see, look at this idea. So in this interval, if you start from 1.45 and going to the 1.55, if you pick any number in this interval, and if you run that numbers, you will get 1.5 all the time. So if you pick any number in this interval like X, and if you run that up to the 10th place, that give you 1.5. You see, that's exactly what you did over here. You see the way we did it? So you just pick in this interval, you see, if you pick any number in this interval, and if you run that up or run that down, you see X goes to 3 positive or 3 negative, you eventually get the 6 over here. So that idea of the rounding is a kind of estimation that we're going to do, and that's going to be the preliminary for the calculus. But the way we are going to do it in calculus, we can do it at any estimate that you like, up to the 10th place, up to the 100th place, etc. So the rounding is going to be a kind of estimation that we are going to use for the notion of the limits. But it's a very special one. We get to up to the 10th place. So up to the 10th place, up to the 100th place is going to be your tolerance. It's going to be the interval that you allow you to go to the right, to the left. That's why you always fix on 5. You say that if the next one, the next digit is bigger than 5, you add 1 unit. If it's going to be less than 5, you forget it. That's why, because you are here, okay, to get these numbers. So it's like when you go shopping. When you go shopping, you know, if something is 99 cents, if you produce the dollar, you're not going to wait for the change because your tolerance is 1 cent. But if you produce $100, you are going to wait to get your change back because your tolerance is not going to be $100. You see, that's the range of estimation they're going to have. So that range of estimation, they refer to it as a percentage of error. So when you do the estimation, you consider that part to be error, but you accept that your error is going to be up to the, okay, it's okay to be up to the 10th place to get these numbers. So that would be a very good idea. And that's just a preview for calculus, really, for the notion of the limits that we're going to do. So in the case of the limits, we are going to estimate the number. Okay, the X would be given to you. You estimate the value of the X when they're getting closer and closer to the 1.5. 1.5. But in our case, there is not going to be any restriction here up to the 10th place, etc. I'm going to use this one to explain a couple of complicated problems in this course. But that gives an idea that you're already familiar with the notion of the estimation or the notion of the limits that you're going to use in everyday life. Any question? So let's give you what is officially the limit of the function. Okay, so that gives you an idea. And let's give you this definition, then we give you your break. Okay, so This is a very important part of this course. And again, at the end of the day, you are going to have a theorem. We call it computing theorem. You use that theorem in order to do all the problems in this course. But if you intend to take calculus 3, especially calculus 3, in calculus 3, you are going to, okay, to extend, generalize these notions. And there is not going to be easy formula to do it. You need to understand the concept. So the concept in detail is going to be used in calculus 3. In calculus 1, we let you go and we work with the formulas. But over there, and if you're going to be a math major, of course, you need to know it. But we want to make sure that we understand the concept. It doesn't matter whether we want to take calculus 3 or not. Okay, just let me know if you need any more explanation. Let's give what is officially the limit of a function. You see, this concept was puzzling mathematicians for years. So don't worry if it takes, it takes mathematicians 50 years to understand it and to modify it if you like. So it may take you the next 8 weeks, okay, the good idea of this idea. So don't worry, be patient. Okay, so I'm going to use some notations. I've already used some of them. Okay, so let's talk about these notations first. That will help us. The limit notations that we use. Okay, is like the one that I did, estimated from the right, from the left. So I get some formula for it. So suppose in your book, they talk about these later on, but we want to do it right away. Suppose a number is given to you. Okay, a number, let's say A, it's a fixed number, is given. I'm going to use a couple of notation. If this is going to be the case, then the first notation is I'm going to write, or we write. Okay, we write x goes to a negative. So this means we estimate the value of the x when they are less than a, estimated from the left. So this means the expression is, we say that x approaches. Okay, x approaches the number. Okay, approaches the number a. Okay, from the left. From the left. So it's not a sign, it's a direction. Okay, left. Okay, so this means, so mathematically, this means the x can take any value which are going to be less than a. So x can take values that are less than values that are less than a, but not equal to a, but close to a, if you like, close to a. Okay, so basically, again, when we write x goes to a negative, so this means it's an if and only if x is less than a and x is close to a and x is approximate. This is the way I'm going to use it. Okay, so this is what we have. So basically, this is the number line and this is the number a. We don't focus on a, so you don't have the a, so you go from this direction, So this direction, this is means x goes to a negative. Any question? So we're using this notation from now on. X goes to a negative means you estimate the a by the values that are less than a. We don't care about the a, okay, because we estimate it. We are not interested in the exact value. So similarly, if you change the direction, we have this notation. So similarly, x goes to a positive, means the right direction. Okay, so this means X approaches, okay, approaches A from the other direction, from the right. Okay, so that's it. Again, this is A. We don't care about the A, but coming towards the A from this direction. Okay, so if we write X less than A positive, sorry, X, we are going to write X goes to A positive. So as soon as you see it, you conclude that if and only if X is greater than A, bigger than A, and X is almost A. Okay, so for the estimation from the right, we write X goes to A positive. For the estimation from the left, X goes to A negative. And we write X, okay, X goes to A. So this means we are going to estimate the value of the X closer and closer to the A from the right and from the left. Okay, so this means these expressions are historically used by Newton again. X approaches, okay, approaches A if you like, from both directions, from the left, okay, and the right, and the right. Okay, so basically this means, so if they write X goes to A, you have to check both of them. So this means if and only if X goes to A negative from the left and X goes to A positive. So that will, that will help us quite a lot to be able, to continue. It's like those rounding that you do, okay? As I talk about, these are all estimations. When you estimate, you may gain something or you may lose something. Okay, this is a percentage of error. So it depends from which direction I'm going to estimate it. But in both cases, when you run the tab and you estimate it, you would get to the target that you have. Okay, and our target is going to be the A that you're going to have. Okay, so that notation would help us quickly to take care of the limits. So I give you a break, 10 minutes. It's a 9:16. Then we come back and we get the official definition of the limit of the function. Okay, any question? So see you at about 10, 12 minutes, and then we continue. Okay, so we are going to continue. So let's so that's the notation. So you say this is estimation for the variable x. Since we have a function, you see if you have a function y equal to the f of x, when x is moving around the a, this is going to be the x is the input. So you're going to have your output. Your output would be f of x. So the value of the x would be considered as the inputs. Then we are going to check the behavior of the outputs. So maybe the behavior of the outputs would be, again, getting closer and closer to the specific number. That specific number would be the limit of the function. Okay, let's give you the officially what is the limits of the function. Okay, we start with a kind of informal definition, and then as we move on, we may come back again and just give you a little bit more tricky one in case you want to take, calculus, especially calculus 3. And so this is officially what is the definition of a limit of the function. We're going to have a function and we want to estimate the value around a given points. Okay, so let's start with the function. Suppose you have a function f is going to be defined near a number a, is defined near a number a. Near a number a means this function is defined around the a. We don't assume that the f is defined at a. Even sometimes you may get the fact that f of a does not exist, but it doesn't matter. We are interested in the values around a. If the function is also defined as a, that's fine, but we don't require that one, okay? So this would be the first thing that we have to consider. So this means f is defined. F is going to be defined because we want to estimate it for all values close to a, around a, around the number a, but not at a, but not at a, at x equal to a. So basically when you say x close to a, this means x is not equal to a, and a is close to the a. Okay, we estimate it. So that's the first thing that we have to consider. So that's it. If you have another number, if L is going to be a number, we see a number, then we write, we write the limit of f of x when x goes to a is equal to the L. Let's say, so this means if you estimate the x by a, then f of x can be estimated by L. Remember, it's a function. So you go to the right, to the left of the a. But at the same time, the output would move around the right and the left of the L. So if when x getting closer and closer to the a, then f of x getting closer and closer to the L, see that the limit of the function at a is equal to the a. Okay, it's like you're rounding the numbers. That's going to be getting the numbers, the values for the x. You round it up and down to the a. Then there is going to be the reaction to these values, f of x. Then your f of x would be again rounded up or rounded down to the L. So if this is going to be the case, we say that the limit is equal to the L. So we write this definition to means if and only if, okay, the values of f of x approaches, if you like. This is exactly the expression that used for the first time. Approaches L whenever, okay, whenever x approaches, I've already defined what you mean by approach. which is A. Okay, so this in short form. In short, this means f of x is approximately equal to the L, but f of x can be estimated by L whenever x is estimated by A. Okay, it's a kind of informal definition that we have. Two arrows means even or live. Okay, so this means equivalent. Okay, even or live, equivalent, yes. They are going to be the same. Okay, this is very informal. Then I come back to it and I put it into the format that we used in Calculus 3. So we're just going on with this estimation that we have. So as we talk about it, you run that, you estimate. When you run that estimated, you lose something, you gain something. The difference between the rounding and this one is there is no restriction. When you round, of course, if you consider rounded the value up to the 10th place to the A, so there is going to be a similar one for the L over here. But when we get the limit, this means it doesn't matter whatever you do. It doesn't matter how are you going to estimate the values around the A. The value of the f of x would be estimated by L all the time. Okay, I'll give you more examples in a minute. Okay, so this is going to be the informal case, and then we estimate the informal one, and you have some preliminary problems in your book, and this is the way we're going to do it. So initially, we want to find the limit. Okay, this is the limit. And the limit is, what is the limit of x squared? Okay, minus x plus 1, and when x goes to 2. Okay, this is our first time that you see this type of problems. So for the time being, the way to do it, we're just estimating. We have to pick some numbers. We have to go to different direction, getting some numbers to the right of the 2, to the left of the 2, and estimated what would happen to the x squared minus x plus 1. Okay, so for the time being, this is going to be our job, but we are going to check it later on quickly. So you have some problems in your book, and this is the way you do it. So you have to estimate, this is going to be your x, and this is going to be f of x. You see the target is 2, so you have to estimate it from the right and from the left. So I'm going to do it from the left. So I put the 2 here. I circled the 2, so this means I'm not going to use it. So get some range of the estimation. Say, must be close. So the range that we pick are going to be between 1 and 2, for example. So pick some values. Okay, these values are arbitrarily. You can pick anything you like. Okay, that is going to be the case. So I said with the 1, you have to use your calculator to substitute here. Okay, if you put the 1 here and you substitute 1 minus 1, 0, that give you 1. Okay, you get closer to the 2. The numbers that I used my calculator previously, so 1.5. So you substitute 1.5 with the calculator, that give you 1.75. Okay, getting closer, something like 1.9. If you put the 1.9 using your calculator, that give you 2.91. Enough number to be able to estimate. So 1995. And if you put the numbers, that's going to be 2.985. So that gives you an idea that if you round these numbers up to the 2, then these numbers over here would be round up to the 3. Okay, so officially this means the limit. Okay, the limit of that function, we call it f of x. When x goes to 2 from the left to negative is equal to 3. Okay, you just pick a couple of numbers to just make sure you are able to estimate it. So we say the left limit is equal to 3 so far. Any question? You have to do it again. These numbers are all arbitrary. Okay, so we pick another one, the other direction. That would be our other direction. This is going to be the x, and this is going to be f of x. Then you have to, you want to do the other one. X goes to 2 positive, so getting closer and closer to the 2 from the right. So we get the 2 here, circle it, make sure you don't use it. So pick something between 2 and 3. The range, again, is arbitrary. You can pick anything you like. So I'm not going to use the 2, something close to 2 from this angle. So it's going to be 2.001. Substitute, use your calculator. That should give you 3.003. Then you get the number 2.005. Remember, you want to run in this direction. And so if you use calculator, that give you 3.015. And I pick 2.1, for example. In the calculator, that give me 3.31. And if you put 3, that give you 7. But remember, the direction is going to be this part in this direction. So if you run these numbers, run the down if you like. If you run the down, that give you run the down to the 3. So this means the limit of the function, the right limits. So this means the limit of f of x when x goes to 3, this time 2 positive. This direction, 2 positive, it's happened to be equal to 3 again. So since from the 2 directions, right and the left, you get the 3, so this means that the limit is 3. So you explained it that the limit of f of x when x goes to 2 negative is equal to the limit of f of x when x goes to 2 positive, and this is equal to 3. So the conclusion is going to be the given limits, limit of x squared minus x plus 1 when x goes to 2 is equal to 3. If you get 2 different numbers, when you estimate it, the limit does not exist. And there are going to be cases that you may get 2 different numbers, okay? So you find the right and the left limits. If they are going to be the same, so in that case, you are going to have a limits. Any question? Again, these are just, preliminary steps. And of course, we are not going to find the limit using this type of ideas. This give us a good understanding of those estimations, and we are prepared for it. Okay, any question? We are going to give you a theorem in a minute, but before getting that, there are some problems in your book. They don't give you the value of the functions. They give you a graph of the function, and they ask you to find these ideas, limits. So I give you one, so get the idea. We're not going to do a graphing one on the test, but it's nice. Some people are getting it better when there is a graph and a display of the function. Visually, so that's why we check this one. Okay, already. So giving you, and then I put it in algebra, and that would be our first question. So example, do exactly the same thing that I did, but this time only the graph. So suppose only the graph of the function is given. So that's our second example. Suppose we have the graph of this function of, okay, the function is y equal to f of x is given. Let me finish the graph, then you draw it. Okay, so this is the graph that we're going to have. You have quite a lot in your book. Just check a couple of them, not bad, to make sure you are able to read the information from the graph. So what I have is going to be, I would like to get the number 2 here. That's going to be 2. Then I put a graph here. So this is one portion of the graph. And then I pick another number. Okay, so I'm going to give you this this number. Okay, so this number is going to be almost okay, this number is equal to 3, for example. Okay, that's 1. And then I pick something here. Okay, and this is the second one that I have. So this number over here is 5. So that was a 3 and 5 that we got. Okay, then I am going to give you, this is the 2, then we get the 3 here. Then I need another number. So what is going to be the next graph, like to something like a 6 here. So that's going to be 6. And then we get these points. Okay, and this point is given to, suppose this is going to be 7. Okay, so this is what we have over here. Let's see what else do we need. Okay, that's enough. So this is going to be the graph of the function. The function is given to you. So they ask you to find the following. Find each of the following. Find each of the following. Okay. We find each of the following are going to be the first part. Would they like you to find what's going to be the limit of f of x? Okay, limit of f of x when x goes to negative. That's the first part that we're going to be interested in. Okay, and what is going to be the next part that we're going to be interested in is going to be this one. What is the limit of f of x when x goes to positive? Okay, that's the case. And then the third part would like you to get what is the limit of f of x when x goes to 2. Okay, that's it. And the last part is number 4. And number 4, I would like you to find what is f of 2. Okay, what's going to be f of 2? That is the case. And then number 5, we wanted to find what is the limit of f of x when x goes to 6. Is that going to be the idea of this graph that we have it? So I have to make some changes to make sure we get this one. There is a hole here. Okay, and everything else now is going to be right. So it's a graph of the piecewise defined function that you're going to see in a minute by giving you the algebraic formula. But we want to do it just using this graph that's given to us. Okay, so as we did it for the other part, so for each part you have to pick some numbers, but you can pick it on the graph to get there. Are you ready? Limit of f of x, x goes to 2 negative. You see this is 2. 2 negative means from this direction. So you have to pick some numbers which is going to be close to the 2. And you check to see what's going to be the number for the y, if you like, for the f of x, to get the limit of your function. You see when x is less than 2, you know that if you want to get this number from the graph, it's the way we do it. If you pick a x here, And if you want to find the value for the y, this is going to be the value for the y. Okay, if you pick another number close to the 2, if you get closer, so that give you the 1. If you get closer over here, okay, so that give you the 1. If you get closer to the 1, that give you the 1. So you have to check to see what is going to be the value of your function, okay? So the value of the function is going to be on the y-axis. You see the numbers on the y-axis, so you pick the numbers close to the a, close to the 2. So these are going to be the numbers down, 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 down. Any suggestion? What's the limit of f of x when x goes to 2 negative? Go to negative. Yes, okay, that's correct. That's a 3. You see when x goes, look at your function. You see when x is less than 2, what's going to be your function? You see this is your function down up here. So the value of the function when x is getting closer and closer to the 2, eventually there are going to be some of those red numbers on the top, but all of them would happen at, would end up at 3 here. So in this case, the limit of the function, you see solution for the first part, the limit of f of x when x goes to 2 negative would be 3. It's like the table that we did over there. You see when x is less than 2, you see if you pick a number here, if you want to find the value of the function, this is the value of the function. If you pick a number here, this is going to be the value of your function. This is going to be the value of your function. This is going to be the value of your function. But eventually you go up to the 2 here, close to the 2, you see, close to the 2, close to the 2, close to the 2. So all these numbers, when you're going down, 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 these numbers getting closer, closer. This is the last point that you did. So everything over here would be round up to the 3. Round up to the 3, so the limit would be 3, the left limits. Any question? So that's first part. Now we do the same thing for the other part. So what would happen if you do it with the other part, the limit of f of x, when x goes to 2 positive. So the 2 positive would be your direction is going to be different. Okay, so you have to pick this direction to get this number. Okay, for the other direction, you have to use the green one. So you see, look at the numbers. If you pick a number that's going to be bigger than 2, it's going to be bigger than 2. So what's going to be the value of the function? The value of the function. If you pick this one to be bigger than function, the value of the function. When you're getting closer and closer, you mark down where. You see this green one? The green one would be up, down to the what? The number that you see over here is 5. So the value of your function would going up and down against the 5. So in this case, the limit would be 5. Okay, it's a piecewise defined function. And you pick the value bigger than 2. If you pick the value bigger than 2, so you have to use the green graph. If you use the value less than 2, you have to use the black one. So the black one would end up with the value on the y-axis, which is 3. The green one would end up with the value on the x-axis, which is 5. So the limit would be 5. Any question? So that's the right and the left limit. So the right limit is 3, the left limit is 5. So what's the answer to number 3? Can we have a limit at 2? You see, you estimate from the right and you estimate from the left. Okay, that's correct. See, does not exist. You see, when you estimate from the right and the left, you must arrive at the same number. You get 3 and 5. Both of them are different. So the right and the left limits are not the same. So this means the limit of the function does not exist. Okay, so you explain it that 3 is not equal to the 5. Okay, or the limit of f of x when x goes to 2 negative is not equal to the limit of f of x when x goes to 2 positive. So the limit of f of x when x goes to 2 does not exist. We accept this one does not exist. Okay, but you have to tell us that this is the case. On the test, you can say that, 3 is not equal to the 5. So this means the limit of the function, limit of f of x goes to 3, does not exist. Okay, I'm going to use this expression. So that is going to be does not exist. Don't say no solution right away. You have to explain it for us. Okay, this is like the one we did. You see, this is the one we did for the estimation. It was a polynomial. So the right and the left, you get the same number. When you get the same number, the limit is going to be just the same number over here, 3. But over here, the right and the left limit was different. So that's why the limit does not exist. Any question? So you see it in algebraic form, and that would be your first question on your first quiz. Okay, so that was the limits. Now, how about f of 2? You see, this is estimation. We estimate the value of the function around the 2, but how about the exact value? F of 2. Look at the graph. What is the value of the function at 2? Any suggestion? You see x equal to 2, you know that to find it. You get the vertical line. That vertical line intersects the graph at 3 here. So the value of the function at 2 is equal to 3. So the part 4, f of 2 is equal to 3. You know that in your previous course, or just if a function is given to you, use the vertical line in order to find the value of the function. You see, you cannot find it from here because there is a hole here. There is a hole here, so you have to find it from this one, the solid point. And the solid point is equal to 3. So f of 2 is equal to 3. Question? So that gives you a better understanding to analyze it. And in future, in your job, in your field, discipline, you do experimental work, and most of the time you get the graph. So you should be able to analyze the graph. Okay, so how about this number part 5? What's the limit of the function at 6? Look at the 6. You see, this 6 is not a partition point. 2 was a partition point. So when it's a partition point, you got to be careful. You have to break it into 2 parts. Because for the partition point, if you go to the right, you have to use the green graph. If you go to the left, you have to use the black graph. But when we get the 6 is just on the green. So you don't have to take the right and the left. You can estimate it by the value of the function, which is the 6. If you go to the right to the left, the limit of the function and the value of the function are going to be the same. It's 7. Okay, so for the right and the left, you have to be worried about it if it's a partition point, breaking point. But when it's not, it's clear. You see, if you clear that, if you go to the left and the right, if you get some numbers here, so it's close to the 7. If you get a number here, it's close to the 7. So if it is not going to be partition point, it's going to be just one part, and then you're done. So the limit of f of x when x goes to 6 is the same as the value of the function, which is equal to the 7. It's very nice examples, okay? And you have everything you need. And just pay attention and pick a couple of them in your book. You have quite a lot in that sets of assignments that you have. It's good for, for your understanding for future. But on the test, I don't usually give the graph and we just go with the algebraic format to get these numbers. Any question? So, this is the elementary tools, if you like, and the tools that we just using those tables to get the estimation, and this is going to be the graph. Of course, if the function is getting complicated, we are not going to use this type of methods. So what we need theorems, okay, machines to be able to do it. So the machine is going to be the next theorem. Okay, this next theorem is going to be very essential to your work. Okay, that will help you to be able to find the limit of the function, and later on of course, for the derivative and whatever we want to do in this course, okay? So it's very important theorems, and you should be able to do almost all the problems, not all of them, yeah, all the problems in your first quiz, just using the next theorem. Okay, so let's get more practical if you like. Now, nice theorem, probably we are in 11.3 now. Sorry, 1.3. So I'm going to call it, we call it computing theorem because you can use this theorem in order to compute any limits in this course, okay? So don't miss it. Very nice result. Computing theorem. Computing theorem. Okay, now, as I told you, you can use it to compute any limit for us. What is this theorem? It's a very easy theorem, really. You see, when we work with the functions, there are some operations that you're going to use. It's like numbers. You add, subtract, multiply, divide functions. So addition, subtraction, multiplication, and division. Or dividing the functions. You may take the square root, the fifth root, 6 roots. So these are the operation with the functions. And the new operation that we produce or we suggest today is the limit of the function. You see, this theorem will tell you that those operations and the concept of the limit or the operation of the limits commutes. Commutes means the limit of a sum of two functions is sum of their limits. We switch. Limit of the product of the limit. Limit of the quotient of the limit. Limit of the square root of the limits. Limit of the fifth root of the limits. That's the idea of this theorem. That's it. Computing theorem. Okay, so that will help you quite a lot. So I'm going to list that. So officially, this is going to be your first tool in this course. So that's it. So we start with the two functions and the two limits. So suppose the limit of f of x when x is equal to the a is given to you, we call it L. And the limit of g of x, the second one, when x goes to a is given to you, this is equal to the m. So one of them is 2, the other one is 5, for example. That's what. Okay, if this is going to be the case, then we are going to have the following. Then the first one, addition. The limit of the sum, you see the limit of f of x plus g of x when x goes to a. The limit of a sum of two functions is sum of the limits. This means we can distribute it. Is equal to the limit of the first one. Okay, plus limit of the second one. That's it. Call it addition property. Okay, limit of the sum of the limits. It's the same as the difference. So if it's going to be minus, it's going to be minus. Okay, so that will take care of the limit of the addition and subtraction. Any question? That's property number 1. Second one. You see, if you multiply a function by a number, 5 times f of x. If you want to find the limit of the 5 times f of x, you keep the 5, you find the limit of the function. It's going to be 5 times the limit of the function. It's going to be used quite a lot in future. So this means if you have a number, if k is a number, a constant we call it, then limit. Okay, limit of the k times your function, k times f of x, when x goes to a, is simply equal to the k times f of x when x goes to a. That's it. So this means if the limit of the function is 2, the limit of the 5 times the function is 5 times 2, which is going to be 10. Okay, so it's going to be used quite a lot. That's a rule number 2. So that's a kind of a product rule. It's a product of a function by a number. Now the actual product rule. Number 3. Okay, limit of the product of two functions. Limit of f of x times the g of x. We call it product rule. X goes to a. Limit of the product function is going to be limit of the first one. I'm sorry, I could write this one as well. You see, this is like k times the limit of f of x is L, k times L. Just to explain it, it's the same here. It's like L plus or minus m. So if you already have the numbers, then you substitute and you get your results. Okay, limit of the product of the limits is equal to limit of the first one times the limit of the second one, g of x, x goes to a. Limit of the first one is L, the second one is M. This is called the product rule. Okay, limit of the product of the limit would be so useful. Any question? Division. Number 4, the limit of quotient. F of x on the top, g of x on the bottom, x goes to a. Okay, if you want to find the limit of a fraction, limit of a quotient, you go up and down. Limit of the top one, limit of the top, f of x, x goes to a, divide by the limit of the bottom one, g of x, x goes to a. So the top is L, the bottom one is M. Of course, you know that when you do the quotient, you must make sure that the denominator is not 0. So we assume that the M is not 0. Okay, so if the limit of the top is 2, the bottom one is 3, so that gives you 2/3. And you're done. Okay, so addition, multiplication by a number, the product of two functions, the quotient of two functions. What else? The next one. If you have radicals, okay, so if you have a limit of the square root, fifth root, 8th root, so n root of f of x, x goes to a. You see, if you want to find the limit of the radical, if you stay outside of the radical, you won't be able to do anything. We go inside. It's going to be equal to the n root of the limit of the inside, limit of f of x, x goes to a, which is going to be the n root of L, whatever we have. Okay, in your book, they divide in 2 parts. They say when n is even or n is odd, but we know that when it's going to be n even, we get the radical -4, we know that that does not exist. So we don't have to, to divide it into 2 parts. Okay, so that would be very helpful to be able to do all these operations. Any question? Now, the big one is the next. Very useful. This will take care of everything we need. See, all the you did here, you can apply to a polynomials. Remember the polynomials? The polynomials is just the powers of x, like x cubed plus 2x plus 1. So if you have a polynomial, if p of x is a polynomial, it's going to be a polynomial polynomial function. You see, then simply the limit of P of X when X goes to A is simply is P of A. You see, because when you have a polynomial like X cubed plus 2X, so what we can do is we can apply all the rules that we have on the top. You see, the polynomial is a sum of powers of X. So we take care of the numbers. The product, if you have a limit of X squared, is the limit of X times X. So we can take care of everything. So in the case of the polynomials, and most of the time we are going to have a polynomial, if you want to find the limit of the function, you just substitute. So the exact value of the function and the estimations are going to be the same thing. Like the one that we did, you see, that the example that we did have, you see, look at this example. This is a polynomial. So now, if you want to find the limit, we just substitute. If you substitute 2 squared minus 2 plus 1, 2 squared is 4, minus 2 with positive 2 plus 1 is 3. So the limit is 3 and we're done. So this is the way we're going to operate. In this example, we just want to estimate to explain it. So that's we use these methods, okay? And so if you have a polynomial right away, you just substitute to get the results right away, okay? So this is going to be the case. We need one more to be able to take care of the examples for you. Number 7 is also interesting. If you have a piecewise defining function like this, you see at the partition point, if you want to find the limit at 2, remember, you have to find the right and the left limits. So this theorem would be helpful for this type of functions. So the limit of f of x when x goes to A is equal to the L if and only if the right and the left limits are the same. Limit of f of x when x goes to A negative is the same as the limit of f of x when x goes to A positive, and this must be L. That's it. So if you want to find the limit of the piecewise defining function, you have to find the right and the left limits. If they are going to be the same, that same number is your limits. If they are going to be different, so the limit of the function does not exist. This is computing theorem. There are 2 more expressions that we need, the results, but we can talk about it now. We talk about it later, but otherwise then we set up to find any limits in this course and when we get to the other part of the course as well. Okay, so very important theorems. That's it. That's going to be one. Let's give some examples. Any question? So this is the way.
I have a
yes.
question.
Yes.
On the test, will you let us know specifically how you want to solve it, whether it's direct substitution or you know, finding values close?
No, you have to find it off yourself. You see, direct substitution is a polynomial. So as soon as you identify that it's a polynomial, you just substitute.
Okay, cool.
Okay,
Thank you.
yeah, that's one. If it's going to be piecewise defining function, then you know that you have to find the right and the left limits. Okay, so you know, we leave it to you and you recognize it right away, the way we are going to do it. Okay, so I'm going to show you the examples to say the way we're going to do it. And don't make it complicated. We're just using this theorem, you know, to take care of it. Are you ready? That's it. We should give you something like 13 examples, 13, 14 examples. And they are all important. They are going to use over and over and over in this course, okay? So pay attention, and this is going to be your first serious job. So by the end of today, you should be able to do 3 of those practice problems that we have on your practice quiz, 4 of those really by the end of tomorrow. And then prepare for your first quiz, okay? So we just cover one more section and then we are done with the first chapter. But we are not going to rush again. We want to make sure you understand it. So crucial example. We wanted to find each limit to show you how we are going to do the, the limits. Find each limit. So just use the method that I'm going to use in this example. That's it. That's it. And number one, I give you all the possibilities. The first one, we want to find the limit of 5x cubed minus 2x plus 1 when x goes to -1. That's it. So what type of function is this one? 5x cubed minus 1.
Polynomial.
Excellent, polynomials. And we know that the limit of the polynomials can be found by direct substitution. That's it. Solution. It's the way we do it. Solution. You just write it down. Is the limit of 5x cubed minus 2x plus 1 when x goes to -1. Since it's a polynomial, direct substitution, substitute. Use parentheses when you're substituting, minus 2 times -1 plus 1. Okay, that's it. -1 cube would be -1, that even -5 plus 2 plus 1. Okay, it's a -5 minus 2 minus, it's going to be -2. The final answer, and you're done. That's it. I don't usually, I do rewrite it, but you don't have to. 5x cubed minus 2x plus 1, x goes to -1, so the limit is -2, and you're done. That's it. It's the way we do it. Okay, that's fine. Any question? So don't break it into part. I've seen some people, they break this one to the limit of the 5x cubed minus the limit of the 2x plus the limit of, yes, that's a preliminary steps that we do it without just applying those theorems step by step. But now we know it, polynomials. When you get a polynomial, direct substitution and done. Okay, don't make it complicated. Any question? That's your first category. Second, what's the second one? Radical. Limit of the cube root, 7x plus 1, x goes to -4. The radical function, we talk about it. If you want to find the limit of the radical function, you have to take the limit inside. Okay, limit inside, take it in. So this is going to be the solution. According to the theorem that we have, the limit of the cube root of the 7x plus 1, x goes to -4, is going to be cube root of the limit of the 7x plus 1, x goes to -4. Okay, that's it. What type of function is 7x plus 1? Function?
It's a polynomial.
Polynomial.
That's it, polynomial. So direct substitution. Very good. Just repeat this one so that you know you remember this. So carefully substitute. So that gives -28 plus 1. It's a cube root of -27. And you know that cube root of -7, it would be what? -3. -3 squared would be 9. -3 times -3 would be -27. Okay, that's it. So the limit of cube root of the 7x plus 1, x goes to -4 is a -3. We usually directly substitute and we accept that. I just want to explain it for you. Any question? So that's a type 2. When we get the polynomials to get these numbers. Okay, let's give you a couple of more, just at least one more. This next one is, next group is going to be tricky. And that would be giving you 4 different questions on the next, okay, 4 different cases for next quiz, next test, and even later on. So pay attention to this one. So how about the quotient? You want to take this one, the limit of, okay, the limit of, let's say x goes to -1. -1, and we have 7x squared, 8x plus 1 divided by x squared plus 5 is a quotient function. You know that for the quotient function, you have to find the limit of the top divided by the limit of the bottom one. Okay, what type of functions are going to be the top and the bottom?
Polynomial.
Polynomials, and you know that limit of the polynomials, direct substitution. That's it. So the solution is going to be the limit of x goes to -1. I repeat it again, but you can do it right away. As long as there is an x, you have to write this limit, but when you substitute, you don't. Substitute 7 times the -1 squared plus 8 times the -1 plus 1, and that's a -1 squared plus 5. Okay, simplify the top. -1 squared is +1, so that gives us a 7 minus 8 plus 1. But -1 squared is 1. Okay, 1 plus 5. The top, 7 minus 8 would be a +1, -1. So that gives -1 plus 1, which is 0. And the bottom one is 6. And you know that 0 divided by any number is equal to 0. Some people, they just stop at 0/6, which is not correct. You have to continue and get it. So the limit is 0. So the limit of the 7x squared plus 8x plus 1 over x squared plus 5 when x goes to -1 is, again, you don't have to write this last one, is 0. That's case 3. Any question? No. The tricky one are going to be starting from the next group. I give you one of them so that you think about it, and we continue tomorrow. And that would be, there are some algebraic expressions that we have to use. Any question? No, just give you one, then we continue tomorrow. Okay, so this is number 1, number 3, number 4. Number 4, let's start with this one. Something quick to be able to do it, but we continue tomorrow. Okay, that's it. Let's see what is special about this one. You know that it's a polynomial all over the places. So we have to substitute. If you substitute, what are you going to get?
0 on the bottom, which you
And
can't have.
And on the top? What's going to be on the top? We get 0 on the top and the bottom at the same time. You see, that's going to be the one. 0, 0. Okay, any suggestion for this one? What does it mean, 0/0?
Means we need to look at it more closely and do something
Excellent.
else.
Excellent, that's it, yes. You see, 0/0 is going to be called indeterminate form. It means that there is a solution, but we have to determine. There are many, many, many solutions to this one. But we have to determine which one is the answer, okay? There is something else that we do with this type of ideas at the end of the course, when we learn everything. We used to do it in calculus too, but we changed the idea. Now, in this part, this means, you see, there is a message. Let's see why we get the 0 here. We get the 0 because we put x equal to 1. When you put the 1 into the function and we get the 0, and this means x equal to 1 is the solution of this equation, x squared minus 3x plus 2. And you get the solution if you have a factor. So when we get the 0 on the top, this means if you factor the top, one factor would be x minus 1. Same for the bottom, x minus 1. So the message so far for the 0, 0 is the top and the bottom would have a common factor. What is that common factor? Move the 1 to the other side, x minus 1. You have to go back. You have to factor it, eliminate that common factor, then substitute again. Okay, so that's going to be the message of the 0, 0 from now on. If x goes to -1, the common factor is x plus 1. If x goes to +1, the common factor is x minus 1. Just for your information, is x minus 1 is a common factor. Common factor. So go back. Go back and start it over. Factor it. So it's going to be limit of x goes to 1. I rewrite it, then I factor it. You see the limit of x goes to 1. So you already got the idea of one factor. You see, one factor is x minus 1. And you are going to find the second one. Easy to find. This is 2. -1 times what would be +2. That give you x minus 2. And this is easy, x minus 1 times x plus 1. That's it. The common factor, you can eliminate it. Remember, we divide by x minus 1. And some people, they say, oh, you do it, you have to assume that x is not equal to 1. We say we have the limit. X goes to 1, remember? X goes to 1 means x is not equal to 1. Since x is not equal to 1, we can eliminate it. That's why you have to keep the limit here. Okay, so this is going to be the limit of x minus 2 on the top, x plus 1 on the bottom, x goes to 1. Now you substitute 1 minus 2, 1 plus 1. That gives you -1/2, which is a -1/2. Final answer. That's very important procedure, and we are going to do it. We use it for differentiation. So the limit of the function is equal to the original limit, x squared minus 3x plus 2 over x squared minus 1, x goes to 1 is equal to the -1/2, and then we're done. There are 4 other cases for this one that we have to consider it, and we'll talk about tomorrow. And all the 4 are going to be your tools for differentiation that we have it. Okay, so for the 0, 0 means there is a common factor. What is that common factor? X goes to 1, common factor is x minus 1. So use this factor it, the top and the bottom, eliminate the factor, then you get the result. There are going to be 3 more cases. I'll talk about it tomorrow. Okay, any question? So be prepared for it. Most of the lecture of the tomorrow will be also finishing these examples. So this is number 4. You need something like 10, 8, 9 more to be able to do it. When we're done with all those, then you'll be able to do all the problems so far. Okay, so pay attention and then read it, and we finish it tomorrow. Any question? So if you like,
I have a question real quick.
yes.
I was wondering if you're gonna provide the answers to the practice tests so we can like check our work and make sure we're doing it correctly.
You mean it's early? We talk about it later.
Okay, just
Yeah,
kidding.
yeah. I mean, it would be too early because we want some people to get to it. Yeah, eventually we give you all the answers. Yeah,
Okay.
I mean,
Thank you.
because this week we go with the quiz. Okay. No, I don't know if you want to do it. Okay, I do it later for the practice one. So you focus. You should be able to do the practice quiz now. Okay, by tomorrow you should be able to do almost all the problems of the practice quiz except one of them. So if you want to work, you just go back and check the practice quiz number 1 and even practice test number 1. Question number 1, 2, 3, you should be able to do it. But by tomorrow, then we will be able to do all of them. So on Thursday, we go over the practice quiz number 1 for you, because your quiz would be posted on Friday. It's going to be quiz 1. So we finish that one. Okay, that's the way we do it. Any question? So study this quickly. If you have any question, let me know, because these are going to be our main method, main tool. Okay, I have to go. And if you need anything, email me. See you tomorrow. Bye.
Bye, thank you.
Bye. Have a good night.